In this final video in Chapter 5, we're going to talk about the last reaction, the last elimination reaction, the dehydrohalogenation. And remember, in the preliminary description we talked about how we're going to take a base. I'll give it a negative charge because most of them have a negative charge. We're going to pull off a hydrogen from the beta carbon. We're going to make the double bond between alpha and beta, and we're going to eliminate the halogen group to produce the alkene. Byproducts are the conjugate acid of our base and the halide anion. All right, so here's some common basis and solvent combinations that you see. Probably the most common one you see is KOH in ethanol, but sometimes you see the alkoxide in ethanol. Here's a more hindered one, potassium T-butoxide and T-butanol that is employed quite often as well. Okay, the halogens that you can have here have to be chlorine, bromine, or iodine, not fluoride, and the fastest reacting is the iodide, faster than bromine versus chlorine. And this is, we'll say for now, this is due to bond strength, okay? We'll see some other factors in play here. But carbon-iodine bond is the weakest CX bond. Okay? Okay, so here's a couple of examples here where you can form multiple types of products. And you see, just like in the dehydration reaction, the dehydrohalogenation is subject to State-Zeff's rule. Here we see the most substituted double bond as the major product. Okay, the top case, their possibility of forming three distinct compounds. So that's alpha, this is beta, beta prime, and beta double prime. All of those hydrogens that all of those carbons that I've labeled beta have hydrogens on them. So any of them could potentially give rise to an alkene at that place, okay? And our major product here is this one, which is the tetrasubstituted alkene. Okay, the second most is the trisubstituted, and the least is the disubstituted alkene. All right, in the second one, we have the possibility of forming two different products, and the major product is, again, the disubstituted alkene. If we're looking at stereochemistry here, we'll also see that this is mostly trans. So we're just basically forming the most stable product preferentially in dehydrohalogenation. We're going to see one exception to that, and that's where we have relatively rigid systems, but we'll come to that after we discuss the mechanism. All right, here's the mechanistic hypothesis. It's widely referred to as the Ingold Proposal. Okay, most dehydrohalogenations are second-order reactions where the rate depends on the concentration of the alkyl halide and the concentration of the base. So you see that both of these are important in the rate-determining step. Ingold, many years ago, proposed that basically in this reaction everything happens all at once. The base comes in, starts to pluck the proton off. As the proton is getting plucked off, a double bond is starting to form and the halogen is starting to leave. Here it is pictured in this transition state where we have these kind of partial bonds all the way through. The only, this is I guess we'll call this a 1.5 bond here in the transition state. Okay, what you'll notice here is that in this transition state, it's very conformation dependent. It has to occur from a conformation where the hydrogen that you're eliminating and the halogen are in an anti-relationship. Okay? And this is called the stereoelectronic effect And this geometry is often referred to as just being anti-periplanar. Okay, and the reason that we have this problem, or have this limitation here, is that because if you look at these p orbitals that we're going to be making for the pi bond, they're coming from the CH bond and the CR bond, okay? So the fact that they have to be lined up perfectly in the product means they also have to be lined up in this way in the starting material. Otherwise, it doesn't know that it has the capability of forming an alkene, okay? So you have to align the orbitals in the starting material into the position where they're going to end up in the product. We say that the CH and the CBr sp3 orbitals are growing or evolving into the p orbitals that make up the alkene pi bond. I'm going to show this transition state again, but we're going to actually have the orbitals pictured here. Okay, so hydrogen and bromine are anti-periplanar. Okay, if I go ahead and put in the electrons, let me just put one to each here, and each of these sigma bonds. Okay, so here's the sp3 orbitals at carbon right here. And you can see that in the transition state, the big lobe, they're becoming more equal, the two sides of the sp3 orbital. And eventually, they're going to become completely equal because that's the way they are in p orbitals. Okay, so this is a one-step. Let me go back to this slide. We're going to use this term concerted to just refer to a reaction that's one step. Okay? All right. And another way to express a concerted or one-step reaction, it just means that if we're looking at an energy or a potential energy diagram, something like this, there's only one transition state, a single transition state, reflecting that we have a single step of the reaction, and that all of the reactants, of course, are important in the rate equation because they have to come together. Okay. All right, let's look at some experimental support for the Ingold hypothesis. This is the most famous one right here. Comparison of the rates of 4-bromo, 1-T-butyl cyclohexane. It's very dependent on which isomer you have. The cis compound affords the product 1,000,000 times faster than does the trans isomer. And the explanation for that is as follows. Okay, we have to consider that our 6-membered ring doesn't look like that hexagon, but it actually looks like a chair. Okay, so if we draw the cis isomer in its most stable conformation, we're going to see that bromine is axial, and T-butyl, of course, is always going to be equatorial. It's so big that it really can't be anywhere else. Okay, when bromine is axial, like it is here, and we look on the adjacent carbons, so we'll just call this one alpha. These here are both beta. We see C3 and C5 have hydrogens that are perfectly anti-periplanar to the bromine. Okay, I've shown it over to the right as a Newman projection, but the same general idea. They're anti. Okay, they're perfectly aligned for the elimination. Okay, so in the most stable conformation, this is the conformation that's probably more than 99% of the bromocyclohexane at room temperature, it's already perfectly aligned. Okay, the trans is probably a more stable compound because both the bromine and the T-butyl can be equatorial, but what does it mean as far as the elimination reaction goes? Well, if you look at C3 and C5, these hydrogens are actually gauche to bromine. They're not anti. So there is no hydrogen anti to bromine. In fact, if you look at what's actually anti to the CBr bond, it's actually the CC bond over here. Okay, so there are hydrogens on C3 or C5 that are anti to the bromine at C4 in the most stable conformation. The halogen needs to be axial for the E2 to occur. Okay, if it's not axial, there can't be a hydrogen anti to it. All right, you're probably thinking, let's just ring flip it. All right, but if you ring flip it, you get a very large group axial. So this has difficulty going axial. Okay, so we can't really do this ring flip. This is not a stable conformation since T-butyl is too big to go axial. Okay, so the elimination of the trans isomer here is very difficult, whereas the cis isomer goes quite readily. Let's look at some more experimental support for the Ingold hypothesis. This last thing here is a kinetic isotope effect. All right, so D, you'll see it frequently used in this class, is the element deuterium, which is hydrogen with an isotope of hydrogen with an extra neutron in it. Okay, I don't want to really get into this explanation right now because it's somewhat complex. It's covered in physical chemistry class, but it has to do with something called 0-point vibrational energy. There's a vibrational component to a chemical bond. Okay, and the net result here is that the bond to the heavier isotope is stronger than the bond to the lighter isotope. Okay, so it's harder to break. All right, so when you take the compound that you see here that has a deuterium on one side and a hydrogen on the other, and you just treat it with standard E2 conditions, you get a 7-to-1 ratio favoring the compound that has all of the deuterium intact. So we get this one from the CH bond being broken. And we get this one from the CD bond undergoing the elimination. Okay, so we get more of the product from the CH bond breaking than from the CD bond breaking. This large kinetic isotope effect tells us that CH bond breaking is important in the transition state. We also have the effect of halogen, that iodine is faster than bromine and chlorine. So these facts together are actually really good support for the Ingold hypothesis. The fact that CX and CH bond breaking are both clearly important in the transition state. Plus you also have this orbital alignment issue which we just discussed. Okay, now your task now is to circle every hydrogen that can participate in an elimination reaction in each of these compounds here. You have to also consider hydrogens that are not part of the ring, hydrogens located in alkyl groups outside the ring. Alright, so this is a conformationally locked system. You do not need to consider ring flips. Alright, so the first one, that's the only hydrogen that can actually be eliminated. Okay, so we could have, imagine a hydrogen like that, and this hydrogen and this bromine here would be perfectly anti-periplanar. Of course, this is going to be a fairly free rotation right here. Alright, so that's the only one that can be eliminated. You may be tempted to say this hydrogen's trans to bromine, but it's not anti. Okay, so it has to have a 180-degree dihedral angle, and this is more like a gauche. It actually is a gauche, not like a gauche. It is a gauche. Okay, 60-degree angle between hydrogen and bromine here, and a 60-degree dihedral angle between this hydrogen and this bromine. And the same thing for the equivalent hydrogens on the other side of the bromine. Okay, next one. Which hydrogens can eliminate? Okay, and the one we're going to talk about next, of course, bromine is axial. So it's all set to eliminate, right? And those two hydrogens there can be part of the elimination as well. Okay, they're anti to the bromine, 180-degree dihedral angle. They're anti-periplanar, so there's no problem eliminating those two. Okay, and this one here, bromine is also axial. And if we look at the hydrogens that can eliminate, it's only this one, right? We can only eliminate on this side right here. If on the other side, of course, there is no axial hydrogen at the right place. The axial hydrogen that we had here has been replaced by a methyl group. Okay, so there's no axial hydrogen there. Okay, here bromine is also axial. We don't have any hydrogens here, so we can't eliminate there. The only place for an elimination is actually in the methyl group, the hydrogens in the methyl group. If we looked at what our products would be, let's just draw them here. From this one, we would expect a very selective reaction for forming this compound. In this case here, we would expect to form a mixture of these two compounds. Okay, we'll just keep the stereochemistry there. Okay, this one here, we're expecting a reaction to make that, and in this last case, we would expect this product. Okay? All right, I know it didn't ask you to predict the product, just circle the hydrogens. I just wanted to show the products of these reactions. Okay, this is a very classical type of problem here. Which compound will undergo the E2 reaction at the faster rate? And this word here, chair, is a very valuable hint as to what the answer is. It's kind of like the experimental proof of the Ingold hypothesis. Okay, so you should pause this and answer the question, and then we'll see if you got the answer correct. All right, so let's draw these in their chair form. Okay, and we're just going to draw the most stable of each of these. Okay, so the one on the left has methyl and bromine equatorial in the most stable conformation. The one on the right side has bromine axial and methyl equatorial. Remember that bromine is not going to be as large as methyl because there are no hydrogens at bromine. All right, so bromine has to be axial to eliminate, right? So bromine's not axial here in the most stable conformation. It is, however, axial if we do a ring flip. However, we expect, if we call this A and this one be A to B is going to be something like 99 to 1. It's going to have a high preference for A, okay? The one that can't eliminate. All right, if we look at the other one, the bromine is axial in the most stable conformation. It'll ring flip. Here I'm going to just say that A to B is probably about 4 to 1. I don't know the exact number here. But what we can see here is that the conformation that can eliminate in A is the most populated conformation, and it's going to eliminate quite readily because bromine is exactly where it needs to be, and it's going to make the E2 product. Okay, another point here is we don't subscript 2. I've been going to try to change that in all my slides. Sorry about that. All right, in this one here, only this very minor conformation can eliminate. So if we looked at the rate, remember, is times the concentration of base. Here, the Rx that's capable of eliminating would be a very small amount, right? 1%, whereas it's like 80% of the conformation at room temperature here. So we're expecting a huge rate difference between these two reactions, and the one on the right should eliminate much faster. Okay, that's a very common type of problem. I think it's some question where you had to figure out if bromine's axial or equatorial, and then look at and estimate the relative rates of the two compounds has been on virtually every exam I've ever given. Okay. In some cases, the elimination doesn't have such a high stereoelectronic dependence, and this is much less common than the E2, but it's also possible to have a first-order elimination, and there's certain conditions on the first-order elimination. The halide has to be tertiary, and the base has to be relatively weak. Okay, in this first-order elimination, the base does not appear as part of the rate equation. Only the alkyl halide appears. All right, so this reaction here is a two-step reaction where in step 1 we dissociate bromide ion to make a carbocation. It's because we're making a carbocation that the halide has to be tertiary. Okay, the carbocations that are derived from primary and secondary halides doing this process are not nearly as stable. Okay. In step 2, which is the fast step of the reaction, the hydrogen is removed from the beta position and we produce this product. Okay, the reason we have to have a relatively weak base is because if the base is strong, we start to see E2 kinetics. Okay, in many of the cases. Okay, so this is the only case where you'd have, so only the tertiary systems would likely do the E1 reaction, and that again you usually would have a relatively weak base, otherwise you would see the E2 reaction start to take over. Okay, let's look at how this relates to alcohol dehydration, and here's the 3 steps of the alcohol dehydration. Notice that the last 2 steps of alcohol dehydration are the same as an E1 reaction, okay? We're eliminating water to make a carbocation, and then we're making the alkene in the second step of the reaction. All right, so I think this is where this video ends.